today on ESIC seminar. Um, Many thanks to Dr. Ben Kroposki from the National Renewable Energy Laboratory for speaking with us today. Dr. Ben Kroposki will be talking about integrating massive amounts of wind and solar in power grids. He is the director of the Power Systems Engineering Center at NREL, where he leads NREL's strategic research in the design, planning, and operations of electrical power systems. He has over 30 years of experience in the design, testing, and integration of renewable and distributed power systems, and has more than 150 publications in these areas with over 8,000 citations. Dr. Kroposki received his BSCE and MSCE from Virginia Tech and PhD from Colorado School of Mines. Dr. Kroposki is the recipient of IEEE Power and Energy Society Ramakumar Family Renewable Energy Excellence Award. This award has been established to recognize outstanding contributions in the field of developing, utilizing, and integrating renewable energy resources in the national and global energy scenario. As an IEEE Fellow, Dr. Kroposki was recognized for his leadership in renewable and distributed energy systems integration. Dr. Kroposki is also an adjunct professor at Colorado School of Mines and University of Colorado and teaches courses on integrating renewable energy into power systems. Let's welcome Dr. Kroposki, and I'll hand it over to you. Thank you.
Okay, thank you very much, and thank you for inviting me to give a seminar today. So before I jump into my presentation here, just want to thank everybody for attending. And then I'm going to switch a couple things. I'm going to switch off my video so that I can save bandwidth while I'm presenting. But if you have any questions, feel free to interrupt me, although I won't be able to see hands go up once I move over to presentation mode. So feel free to just jump back in and ask me questions while I'm giving the presentation. And then we should have some time at the end for more Q&A. Okay.
So Ben, just a quick point. So is it okay if we record the presentation?
Yep. That's good.
Okay, thank you.
Okay, thank you. Okay, so I'm going to go ahead and switch over now. Grab that little laser pointer. Okay, so today I'm going to talk about integrating massive amounts of wind and solar into power grids, and a lot of the challenges that come with that, as well as a lot of the solutions. But to start this presentation off, I want to give some context of what is happening in the electric power industry today, because we are seeing some significant changes that haven't been seen, in the last 70 years. And so we need to really understand what's happening, why it's happening, and then how we can address some of these things. So first off, 2020 was actually a very significant year in the electric power industry. And for the last 10 years, we've seen some significant changes. If you take a look at this chart here, this is from EIA, you can see from 1950 to roughly around 2007, there was this very steady growth in overall load in the power sector and increasing amounts of production from a variety of sources. But in the last 10 years, we've started to see some big changes. First off, the decline in the use of coal has been fairly significant. And then renewables and natural gas have increased, and nuclear and hydropower have remained fairly constant over that last 10-year period. But this was actually the first year that renewable technologies, and so this renewables would include hydropower, wind, solar, biomass, geothermal, it actually produced more electricity than either nuclear or coal. And that is a big shift happening in how we're getting our energy for electricity in the U.S. Now, if we dive into that 20% of energy that's provided by renewables, we can see the breakout over here. 8.5% from wind, 7.3% from hydro, 2.3% solar, the rest from biomass and geothermal. But again, 2020 is a unique year. It was the first year that wind actually produced more energy than hydropower. And over the last 10 years, you can see this dramatic increase in renewables is driven by wind and solar technologies. So this is the big shift that is just starting to occur and is going to continue for probably the next couple of decades, is this large increase in wind and solar use in the United States. Now, what's really the driving force behind this? At the end of the day, if you look at the electric power industry as a whole, it's always driven by developing reliable power systems at the least cost. So least cost electrical system planning has been the heart of the electric power industry from its inception. And the reason that renewables continue to increase in terms of the amount being deployed really goes back to the cost of them. If you go back to the early 2009, 2000 time period, you see that wind and solar were still the highest form cost of electricity. But over this 10-year period, we've seen dramatic declines in both wind and solar, especially utility scale wind plants and solar plants. And right now, wind and solar are the most cost competitive forms of new plants. So if you were going to go out and build a new power plant, this what these costs represent here, you can see that wind and solar clearly are the lowest cost forms of new electricity. Now, of course, this is location dependent because it depends on your wind and solar resource. But if you have good wind and solar resources, these are clearly the most cost competitive. Now, if you take a look at this, as I've been describing, these as if you were to go out and build a new plant, whether it's wind and solar, natural gas, coal, or nuclear power. But these costs actually are so low that they are actually rivaling already installed coal, nuclear, and gas plants, meaning that they produce electricity at a price per megawatt hour that's in a lot of cases better than existing coal plants. And so that's why you're starting to see a lot of coal plants retire, but they're getting very cost to the installed or cost of nuclear and natural gas. And a big thing to mention here is obviously that wind and solar are variable, so their output changes with the weather resource, whereas these other forms of energy are dispatchable. They have the fuel at those sites. So another thing that you have to take into consideration if you want these to be really apples to apples comparison with these technologies is you probably have to add some level of energy storage with these plants. And we'll talk a little bit about that later on in the discussion here. But once you get wind, solar plus storage below any of these costs, that's when they will really take off. So let's continue to describe this. Obviously, economics drives this, but there are a variety of policy factors that need to be mentioned in here. And specifically, we have states that have made their own clean energy mandates. These states colored in blue have some form of clean energy mandate, and the states that are in the dark blue color oftentimes have 100% clean energy mandates. In addition to states making their own regulations, we also have utilities. So these green shaded areas that you see scattered around here, as you can see, those don't nicely line up with state lines. So those are utility service territories that have 100% decarbonization goals. Now, decarbonization would include nuclear as well as renewable technologies. But as you can see, that is a pretty big spread across the United States of policy drivers that are impacting the use of renewable technologies. So as you can see here, just a little background, we are going through a significant change in the power sector. More and more renewables are being integrated into the grid. So let's take a look at what we know today about integrating these variable renewables and how much can be integrated. So first off, we'll take a look at this particular graph. If you take a look here on the x-axis, this represents overall system size. So pretty much the size of the load of these different types of power systems, from very small power systems that could be on the order of, say, 100 kilowatts, up to a megawatt, 10 megawatts, 100 megawatts, up to a gigawatt here in the middle, and then out to 1,000 gigawatts, which is the size of the continental United States. But first off, we'll take a look at small islands and how they're operating with percent of wind and solar shown here on the y-axis. The other thing to mention is these two little colored parts of the graph. First off, this red square, that represents instantaneous power level. So the amount of wind or solar at any particular point in time during the year. So if you had a very sunny day, you could be operating at 100% solar power, or a very windy day, 100% wind power. Of course, that could change during the day. The annual energy is this gray circle, and this gray circle represents over the entire year how much of energy was being provided by wind and solar. And as you can see, for these relatively small systems, we can get very high instantaneous power levels of wind and solar, up to 100%, as well as very high annual energy amounts. And so you can see these are all island power systems. This is a picture of Tau Island in American Samoa, King Island, which is in Tasmania, and El Hierro, which is in the Canary Islands. But you can see one other thing, although it's best represented, I think, in the El Hierro system. This lake that you see in this picture, this is part of a pumped hydro system. So there's a significant amount of energy storage tied into this particular grid. And if you were to look and evaluate all of these systems, you would find that they have large energy storage. This is pumped hydro here and battery energy storage in these particular systems. The other thing to note that even though this is around 150 kilowatt peak load, this is over a megawatt of solar and a megawatt of batteries for that particular system to run at 100% solar and batteries throughout the entire year. But the key thing here is we do know how to operate these small island power systems with 100% wind and solar. And so what we want to do is, as we get larger and larger on these power systems, take some of those lessons learned. So let's kind of move up to the next level. These systems here are what I would consider large island power grids. They range from the Hawaiian islands like Kauai and Maui, all the way up to the country of Ireland. And this is both the country of Ireland and Northern Ireland power system. But as you can see here, we can operate these at fairly high instantaneous power levels and getting between 25 to 40% on an annual energy basis. Now, these types of power systems represent much more what you would consider a power system. They have generation distributed all over the island. They have transmission and distribution systems. They have control room centers where they maintain kind of a watch on the power grid itself. Now, interestingly enough, over time, this was taken in 2019. Just this year, we've seen both Maui increase the instantaneous level of penetration up to about 90%, and Ireland moved from that 65% up to 70% instantaneous levels. So these numbers are getting higher, and obviously we need to do some more work to get them even higher, up to and close to 100% instantaneous levels, so that these annual energy levels can get above 50%. Now, as we look at really large-scale power grids, what you see here is the ERCOT system, or the Texas grid, as well as the Western Interconnect of the United States. And you can see the power levels here range from 26% annual basis and instantaneously up to 58%. And then the Western Interconnect, this is 2018 data. I just saw some data earlier that showed this actually went from 13 to 36. And actually, ERCOT is now operating 66% instantaneously as of March of this year. So again, we're seeing the increases happening even on the larger power grids with more wind and solar being deployed. So to kind of summarize where we are on this particular graph, you can see that on small power systems, we know how to operate with extremely high levels of wind and solar, and as they get larger, not so much. But that's a function of a couple of things. One, of us just integrating more wind and solar into these real scale grids, but also understanding the challenges with integrating at higher levels. And so one of the key things that we need is we need to develop better technical solutions to get to 100% inverter-based grids in any scale power system. So if we could operate the Western Interconnect with 100% instantaneous levels of inverter-based resources, that would really help the overarching annual levels get fairly high and above 50%. And the key to doing this is really, and I'll go back to this several times, is unifying the operation of the inverter-based resources and the synchronous generator-based resources. Another thing that I wanted to just put out here was another particular graph from a different part of the world. So this is actually the Australian power grid. And for the most part, the main power grid in Australia is this one that runs along the southeastern and southern and eastern coasts around here where their major load centers are. But if you take a look at just this piece of the grid here, which is called South Australia, this piece, you can look at a particular day in October of last year where they were actually running 100% on photovoltaics. So you can see the underlying load is this red dashed line here, and then this represents the amount of solar from distributed rooftop PV, and then this darker color yellow is the amount from utility scale solar. And you can see that they reached a couple hours in here where they were running 100% from inverter-based resources and specifically solar. Now, if you also take a look in here, you'll see that they did keep some natural gas plants on, and then they could export that energy from the South Australia part of the system over to, in this direction, to New South Wales. But the key piece here is that this futuristic scenario of lots and lots of solar and wind is happening right now. And so in Australia, they're seeing these type of events happen on a regular basis. But note that what we want to try to do is solve this problem in such a way that we could actually turn these gas plants off and have the wind, solar, and battery be the 100% grid in that particular case. But right now, just because of the stability margins and a variety of other things that I'll kind of talk about here, they're having to keep this natural gas plant on and export that energy. Okay, so let's talk about this challenge of getting to very high levels of instantaneous inverter-based resources. So if we think about how the power grid works, what we have built over the last 100 years is this idea of connecting multiple synchronous generator-based resources together. So hydro plants, nuclear plants, coal, natural gas, they all at their heart have a synchronous generator that connects electrically to the grid. And when you tie these electrically together, you are creating an electromagnetic coupling between all the synchronous generators. They're actually synchronizing together and rotating in such a way that they produce an AC waveform. Typically it's 60 hertz here in the US, could be 50 hertz in Europe, but these are all connected together. And for example, if you were to lose one of these plants, the other plant is still connected and would have to pick up the slack from that. That is sort of this idea around inertia in the system. And so the inertia in the system is this ability to respond to changes in load or power and have everything react to it. If you're interested, I'll just point out there's a cool little video that you can Google. It's on YouTube called Understanding Inertia. And it explains sort of this overall concept with inertia in the power system. Now, when we connect other types of devices, induction machines or inverter-based technologies, they don't have the same kind of makeup as a synchronous generator, so they have a different kind of physical coupling to this large power grid. But what we want to be able to do is design our inverters that are from the PV systems and wind plants and battery plants in such a way that they mimic some of the operational controls from synchronous generators so that they respond quickly to events happening and replicate some of those inertial characteristics. And so we really need to, again, unify the operation between synchronous generators and inverter-based resources at any scale. So I'll point out a little example here around system stability and why this is important. So if we take the Western United States, shown here in this particular figure. And if you look at some type of event happening, if you're losing a large generator or you're losing a transmission line, we call these contingency events. And so what we're going to do is look at the impact of a contingency event on the Western United States and then see how the entire system responds when we enable wind plants and solar plants to provide voltage regulation and ride through that particular event. So in here, what we'll do is we'll drop out a transmission line and we'll see what happens. These little colored dots represent voltage levels. And then this graph right here is representing frequency. So what's going to happen in time, we're going to open up a transmission line. You'll see the frequency dip, but then you'll see we'll be able to recover from that. So first off, we'll open up the line. We open this line. That causes a voltage dip in the middle of the Western United States and also a frequency dip. But these plants are set up in such a way that they can respond very quickly to that and start to pull the rest of the system back into synchronization and recover that frequency. So as you can see, even though this line opens up, the power starts to reroute, and we're able to eventually get that to stabilize back around 60 hertz. So this is key in understanding how deployments of inverter-based resources will impact large-scale grid stability. And so we've demonstrated that even with a major contingency outage and 30% on an annual basis is being provided by wind and solar, that you can survive these type of events. We've also done some real-world experiments. So this is not just modeling and simulation, but going out to actual plants and demonstrating that they can provide some of these grid services. In this case, we went and worked with First Solar, which was the developer of this 300 megawatt PV plant in California, and CAISO, which is the California system operator, which manages the grid in California. And as you can see what we did here in this particular demonstration, so before this plant went into full-scale operation during commissioning, we actually worked with the developer to demonstrate that we could provide what we call up and down regulation services or following an automatic generator control signal. So if you take a look at this graph here, you see this green line. That represents the available megawatts of this plant at peak power. So you can see it's kind of going up in the morning here based on how much sun is available, around 200 megawatts. But what we did was we actually, using the inverter controls, pulled off the peak power point and derated it roughly 30 megawatts, so about 10%. What this enabled us to do then was then receive signals from the California system operator to either inject more power or reduce power. And by doing that, what you're doing is changing the system frequency. So as you inject more power, your system frequency will change. As you pull off power a little bit, again, your system frequency will adjust. And what you're trying to do is manage your system frequency to maintain a 60 hertz profile. So typically, the large-scale coal plants, gas plants, et cetera, do this type of fast regulation services for the system operator. And PV plants and wind plants have not been required to do this. But what we wanted to demonstrate is that these inverter technologies actually have this capability. And not only that, they actually respond extremely well to commanded signals. So in the future, as we look for wind and solar to play an ever-increasing role in the grid, they will have to provide these essential grid reliability services to maintain stable operations at high levels of inverter-based resources. So we've done it for large-scale solar plants. We've also shown this for large-scale wind plants. We worked again with CAISO, General Electric on the Thule wind farm, and showed that you can actually pull on and off power in relationship to available signals coming from the system operator. So there are a variety of technical challenges that you have to deal with when you're thinking about integrating these inverter-based resources. So I've kind of, at a high level, talked about system inertia, frequency stability, voltage stability, and regulation. I'm going to skip these two, and I'll come right back to them, but I'll talk about system protection real quick. So system protection, what that means is we need to be able to recognize fault conditions in the grid and respond appropriately. And a lot of times we have built the past protection systems on the fact that synchronous generators are able to provide a lot of fault current when they're under a fault condition. That can be seen here in this example where if you had a normal operations and then all of a sudden a fault, your synchronous generator potentially could provide a huge surge in fault current. Now, that particular characteristic allows us to look for this large surge and do what we call overcurrent protection. So we can measure very quickly, see this large fault current happening, and that tells us something is going wrong in the system, and we can start to use protective devices. But with inverter-based grids, you can see here, even if you were to implement the same type of fault, you can get a variety of responses. You can get this really fast response here that's shown in red where it sees the fault and disconnects very quickly and goes to zero. Or you could ride through the fault and you would get this green characteristic. Maybe it rides through for 7 cycles and then trips off. But in either of these cases, they don't look like this blue graph. And so coming up with protection schemes for how you have high inverter-based grids is going to be a critical piece of research here in the future to develop these different types of protection schemes so that we're not completely dependent on overcurrent protection. The other 2 things that I'll mention here are grid forming capabilities and black start. And to talk about these a little bit, actually I'm going to show a little video. So hang on a second here. I'm going to see if this works.
As solar and wind installations soar, we hear doubts about operating large grids with high levels of renewable energy. Critics say wind and solar are too variable. What happens when the sun goes down or when the wind doesn't blow? Renewables alone cannot recover from a blackout. But at the National Renewable Energy Laboratory, these doubts don't line up with our experience. We've powered one of our campuses with 100% wind, solar, and batteries, and our approach can extend to much larger systems. In fact, we have clear technical solutions to reach full renewable operation on systems as big as state or regional power grids. And with some of our partners, a 100% renewable future is not far away. NREL is validating their options today on commercially available equipment at relevant scales. Using a 1.5 megawatt wind turbine, a 450 kilowatt PV system, and a 1 megawatt lithium ion battery, NREL was able to demonstrate 72 hours of continuous operation of our building's load using only renewable energy. This animation shows real data from NREL's 100% renewable energy power system operated throughout a single day. Electrical lines are all underground and connect the wind turbine, PV system, and the battery to the building. At the start of the day, the PV system charges the battery and provides electricity to the building. During the day, when small clouds pass by, the battery helps smooth the power to the building. As night falls, the PV system stops producing energy and the wind turbine starts. At night, a mix of battery and wind energy is used to power nighttime loads. Note that the battery is again used to smooth the power provided to the building, thereby providing continuous power from a 100% renewable energy. One unique aspect of this demonstration was the use of innovative controls that do not require any communications between the wind turbine, PV system, and battery. This concept of zero communication is scalable to much larger applications, like the islands of Hawaii, where NREL is helping transition to 100% renewable, or on larger mainland power grids, like the Western Interconnection that spans the entire U.S. West. Finally, NREL was able to demonstrate the ability of this type of system to start from blackout conditions using grid-forming inverters. This capability will be critical for ensuring overall grid reliability. At NREL, we are using the Advanced Research on Integrated Energy Systems Research Platform, or ARES, to demonstrate large renewable power grids. ARES combines a variety of technology types, simulation capabilities, and data resources to evaluate advanced concepts on actual energy systems. Our results with ARES suggest there is nothing to fear about a fully renewable grid. With the right design and controls, renewable energy stabilizes, energy efficient, and resilient at any level on the grid. And with innovative tools and real system examples, NREL is showing how to make this a reality. Learn more at www.enbridge.gov/various.
Okay, so hopefully that came through and you could hear that. But again, what we want to highlight here is that we actually have set up a fully 100% inverter-based renewable power system and demonstrated that we could do black start or grid forming capabilities with that. So what that means is that if the entire system went down, we could restart it with these inverter-based resources. And we also demonstrated, as it said in here, 72 hours of running this particular system during a site outage. And so we really think that it's important to think about, okay, we can do this at, megawatt scales level. How does this scale to much larger grids? And we've demonstrated some ideas on how to do that. Along all of these lines, actually, there's a new consortium that we are getting ready to kick off here in January called our Universal Interoperability for Grid Forming Consortia, or UNIFY, where the idea really is to unify the integration of inverter-based resources with synchronous machines. This is co-led by NREL, University of Washington, and EPRI, and it's really to address these fundamental challenges of seamlessly integrating grid forming technologies into future power systems. And we have a large portfolio of projects that's going to run over at least over the next 5 years, and then hopefully be sustainable after that. But bringing together a large number of partners into this space to develop sort of the rules of the road around this future energy system. So in addition to all of that with the inverter-based resources piece, I wanted to talk a little bit about just dealing with variability and uncertainty of wind. And this is sort of the challenge that you have with longer time scales. So it's balancing when you have wind and solar with a variety of different options. And what do we mean by that? If you take a look at this particular video, what it's showing you is sort of a day in the life of the eastern and western interconnects with large amounts of wind and solar. So represented in here, all these yellow dots are solar plants deployed across the U.S. The blue in here is wind. As you can see, the nightfall come. The pink plants are natural gas plants. The coal in black and the red is nuclear, and hydro plants are these light colors here. As the sun comes up, you can see the solar plants come online. The interesting thing here, and this is looking at a futuristic scenario of large-scale deployments of wind and solar, is all the flows of energy around the eastern and western interconnects in the United States. So on the right-hand side, you see the eastern interconnects and various power flows between different balancing areas, and on the western interconnect, the various power flows. Again, as the sun comes up, you can see, for example, the solar energy is getting pumped out of the southern United States up north and the like. But the key point here is that at every time period, we need to balance generation and load. And so there's a variety of technical solutions to enable this futuristic scenario. This graph right here kind of talks about the variety of different options for dealing with this variability and uncertainty and creating the system flexibility necessary to enable large-scale deployment of renewable technology. And we're going to jump in and talk a little bit more details here about each of these. So first off, you think about the existing generation that you have. And we spent a lot of time at the beginning of this presentation talking about wind and solar, these inverter-based resources, and all the services that they can actually provide to help support the grid. And these are important as we get more of these different technologies integrated into the grid, that they'll have to step up and provide some of these essential grid reliability services. So as we decrease the number of conventional power plants on the grid, it's also important to understand what kind of ramping capability do these have to deal with the changes and variability of wind and solar. Another important thing to consider is demand response. If we think about the demand on the grid, historically, we've always just let the grid do what it's going to do in terms of load. And whether it's residential, commercial, industrial, or even the new electrical load of transportation as we electrify vehicles, we haven't really placed too much demands on the load. And to integrate more variability in wind and solar, we may want to look at how do we actually make the loads more responsive, whether that's at the industrial level all the way down to individual homes. But when you think about that, it's interesting to think, well, wait a second, that's potentially, a lot of things to control if we're now controlling the loads out there. So how do you control millions of generation, storage, and load? And so we've been doing work that actually looks at the deployment of electric vehicles, buildings, PV systems across large-scale areas. If you think about the San Francisco Bay Area, that may be 10 to 20 million controllable devices that you have in that area. So it's important to come up with control algorithms that would enable this. And we've done large-scale studies where we've looked at the deployment of, in this case, roughly 400,000 deployed PV systems. Each of these yellow dots represent a PV system, 400,000 building loads, and also on top of that, 10,000 electric vehicles, 200 charging stations, how these all work together. And through a concept that we call autonomous energy grids, I won't go through the details too much here in this presentation, but you can check out information, just Google autonomous energy grids and NREL. We've developed these complex multi-domain energy simulations of extremely complex energy sectors with all of this integration. We've also developed and evaluated the use of distributed hierarchical controls that would allow you to do controls of millions and millions of devices at 1 second time resolutions. And so that's considerably different from how we actually manage the grid today, but it's something that we need to think about as we move to the grid of the future. In addition to thinking about stuff at the distribution level, let's go back to the grid itself. And it's important to understand a couple of concepts around how we actually operate the grid, how do we set up balancing areas, how do we do economic dispatch at finer time resolutions, and then also things like how do we actually look at the transmission grid that exists today and improve it to access wind and solar. And I'll point out a study that was completed just a few years back called the Interconnection Seam Study that looked at the increasing the benefit of tying the eastern and western interconnects more fully. So right now they operate really as 3 independent systems. And we evaluated building up stronger ties of the existing back-to-back DC converters. We also looked at putting in large-scale HVDC that would tie the eastern and western interconnects together. And finally, looking at nationwide HVDC concepts. So there is going to be a lot of work in this space right now. There's a big push from the current administration to develop a national transmission plan, as well as evaluate a variety of different opportunities to expand the transmission capacity so that we as a whole can have better access to the wind that runs down the middle of the United States and the solar resources across the southern portion. So finally, the one magic bullet that's out there that people are always talking about, but I want to just show you some relative projections on this, is energy storage, because it's a key component for how we see the grid of the future working with all this variable wind and solar. But of course, storage costs money, and it's also interesting to look at sort of relative sizes of different amounts of energy storage. So the first picture I have over here is at least it was when I made this, the world's largest battery energy storage system. It's a 250 megawatt for 1 hour, so a 250 megawatt hour lithium-ion battery system located outside of San Diego, California. And there are several of these types and scale battery systems that are currently being installed in the US and around the world. But compare this 250 megawatt hours with the world's largest pumped hydro system. This is the Bath County pumped hydro system in Virginia. As you can see here, this is 3 gigawatts for 11 hours. So, roughly 30 gigawatt hours. Many, many times bigger than the battery storage systems. But the problem with this, obviously, you need sites that will allow you to put in these scale of pumped hydro systems. And so we're not seeing a ton of pumped hydro development in the continental United States right now, but it's definitely a technology that brings a lot of benefits when we're looking at the integration of wind and solar. We are seeing large amounts of deployments of batteries, but as you can imagine, it's going to take us a long time to get battery systems that are on the scale of these pumped hydro systems. I'll throw this up. This is out of a recent report that NREL produced that is looking at storage deployment. It looked at basically pumped hydro, lithium-ion batteries, flow batteries, and hydrogen storage. I think the key thing here to realize is just how much storage do we need. So currently we have roughly 23 gigawatts of pumped hydro in the United States, and on the order of about a gigawatt of batteries. But if we look at what it's going to take to get to some of these very high levels of wind and solar, you're talking something like 250 plus gigawatts, which is, 10 times what we have currently installed in terms of pumped hydro. So we have a long way to go in terms of producing and deploying energy storage in the U.S. to accommodate all of this wind and solar. The last thing I'll just point out here real quick is that energy storage, as we start putting in more and more, you can see here we looked at different types of energy storage in terms of how many, for example, very fast energy storage for operating reserves, peaking capacity, and the diurnal storage, so hours, but then looking at the seasonal storage issue. And here's where that's really kind of prominent. So if we were to look at a big power system, the ERCOT power system, where we deployed 92% renewable technologies, you see you got lots of the year where you have excess renewables and big portions of the year where you need energy, and so you need seasonal type energy storage to make this work. And that's going to be critical as we look into these technologies for storage in the future. So to wrap this up, we're seeing this big shift toward 100% clean energy goals, and each region of the U.S. has a variety of different resources to tap in to meet these goals. One way to address this is to increase the use of variable renewables like wind and solar. And the favorable economics are just going to drive wind and solar deployments here over the coming decades. But there's still two big challenges to deal with when we're thinking about getting to these very high levels of wind and solar. First off, the inverter challenge. How do we make sure the grids are stable when we add all of these power electronic-based resources and start removing a lot of the synchronous generators? And then that balancing challenge. How do we make sure we maintain supply and demand over all these timescales? But at the end of the day, if you look at these challenges, we think they're all solvable, but we need to work together to meet these. And that's where we also need a lot of the upcoming students and sort of workforce behind all of this to understand the challenges and be prepared for the next 10 to 20 years of a lot of opportunities in this area. I'll leave you with some references here that dive into some of the details in this area. And with that, I'll say thanks and take questions. So thank you very much.
Thank you, Ben, for very interesting presentation. We have a lot of questions, so I'll start from reading these questions from the chat, and we'll try to get to as many as possible. So the first question is from Brent. It's on slide 4. He's asking, is this US cost only or the worldwide? And does it include the impact of incentive and subsidies? So this is about the renewable cost, the levelized cost of energy that's showing, yeah.
Right, so those costs are based on US costs only, not worldwide costs, I believe. Let me just show this real quick and push up the reference so you can go dig it up. It's easy to go find costs. Lazard's levelized cost of energy, it's up on the web. It's easy to get to. They do a very good job of tracking down the latest costs and explaining all the details behind them. So let me just make sure that you see that reference. Again, it's Lazard. You can Google it real quick. It's probably the best place to get current costs on electricity pieces. It does, to some extent, include, they'll tell you all the details. Sometimes it does include the subsidy costs for wind and solar, as well as other pieces, and there are lots of details when you start digging into actual costs of different technologies that you have to be aware of.
Great. So other follow-up question on the same slide, is the cost consistent with the capacity factor of these resources?
Well, yeah, capacity factor is obviously going to vary depending on resources. So plants like nuclear plants going to have a very high capacity factor, like 90%. Wind and solar plants, wind in the U.S., these are probably average numbers. So average capacity for wind in the U.S. is probably somewhere around 35–40%. Average capacity factor for solar is more likely 20%. So capacity factor, but it does take the average cost of producing those electrons is sort of taken into account with the capacity factor. But that does impact the dispatchability of the resource. And so you do need to take that into account. Again, it's really tough to generalize that a capacity factor is good or bad. It really depends on, do you have the electricity when you need it?
Right. So it's basically the cost of megawatt hour produced, right? Not the installed.
That's right.
Yes.
Yeah, it's a megawatt hour cost of produced. That's right.
Okay. Right. So the next question is on the black start capability. So the student is asking, can you please briefly explain the procedure followed for black start capability test of inverter?
Sure, you turn off the grid and you see if your inverters will restart. Now, of course, when I'm showing our very small system, we have control over all the assets, so we can individually turn them on and off and or disconnect from the grid at will. That's a little different. You got just separate the idea of black start, so having the capability of coming up and forming the grid with a restoration process. So you got to kind of pair those two together. If you're thinking about a large scale grid, you got to work your way through which parts of the grid do you turn on in a specific sequence to restore the entire grid. In our little demonstrations, since we own all the grid and we own all the assets, it's easy for us to coordinate that.
Great. Okay. So the next question is, could you please explain amount of load served during 100% renewable generation, which is basically the test case that you had for your building, right? Also, could you please explain the capital investment from wind, battery storage, and PV to serve the load? Maybe the next questions I can walk through. So this is one of the questions on.
Okay, so first one is we were serving 100% of the load with that power system. Of course, our load, if you take a closer look at that graph that's on that slide, is roughly around 250 kilowatt, and it's very constant. It's just building, lighting, and heating loads. So let me just throw that up here real quick. Okay. So if you take a look in here, you'll see, it's on the order of 300 kilowatts. It's this gray line that's running here. That's the load. It is varying a little, like if we have the heaters on, it'll vary a little bit, but it's fairly constant. And then so that's 300 kilowatts. We have a 1.5 megawatt wind turbine. This green line is the wind turbine going on up and down based on the wind resource. The battery is a megawatt in size, and the battery charging power in and out is this blue line. So, and then the PV system, and this is a clear day except for these clouds, is around 450 kilowatts. So here, as you can see, the PV system is providing power to the load, and then we're charging the battery when we have excess power. And then at night, when the PV system shuts down, the wind turbine we turn the wind turbine on here, and it can be, the wind turbine is going to be highly variable depending on the wind conditions. And then we're back either charging the battery or using the battery to maintain that steady load profile. So hopefully that explains that chart pretty well. Now, costs is a whole different factor because these resources were already sitting at our site for research experimentation, so we didn't pay for any of those technologies. So it's a little misleading to talk costs in this particular case. We just had those, we have those on site for experimental purposes, but we had a site outage, so we used them to power the site while we were experiencing the outage. Okay.
So one follow-up question here is also on what kind of loads was the study done? Were there industrial and motor loads in the test design?
Well, yeah, I'll say this. The test set, there was not much of a test setup or design. It was we lost power to the site because we had a problem with our substation. We were going to be down for a couple of days. And then we just said, well, we have all these assets. We have battery, PV, wind. Can we make it work? And we just quickly reconfigured the grid and got it to operate. But it did include resistive heating loads, lighting loads, small motor loads, no big motor loads, not like a dynamometer or something like that on there. But your regular, I would say, commercial building, office space type loads.
Great. So the next question is from Henry. So thank you, Ben. Great presentation as always. A quick question: how to maintain 10% headroom all the time? Would it need very good short-term forecasting?
Yep. So a couple of things you would need. First, you would also need to make sure that the system operators and owners want to do that, right? Right now they're reimbursed by how much power they put out, not by how many grid services they provide. So that is one of the challenges, at least here in the US. We actually have been able to implement this in Chile, where they have a market for providing that up and down regulation service. That being said, that yes, you would probably, the inverters are so fast that they can, provide, and they're so controllable that they can provide any amount of that reserve that you want. To make sure that you don't get yourself into trouble, you would want fairly good short-term forecasting so you could see clouds coming over the system and the like. A lot of the plant owners could implement that short-term forecasting, and depending on how variable of a day the clouds are having, for example, as you can see, we did it during a very clear sky condition. We did not add the variability of the solar in there. And so therefore, we didn't implement a short-term forecast into the system. In general, you would need a good short-term forecast, and you would probably want to build in that capability to respond to those system changes. Okay.
Okay. So the next one is from Robin. So NERC is saying we need EMTP studies to examine impact of renewable tripping under voltage dips. What are the challenges to run EMTP on large interconnections?
Hey, I just saw a presentation on this exact topic about an hour ago, but a whole presentation. I mean, this particular topic, there is a lot of work being done on this particular thing because of the issues that we're seeing with inverters tripping for a variety of reasons and faults on the power grid. So there are challenges with setting up EMTP models of these large-scale power grids. And the biggest one is probably that once you get to doing things on that time scale, EMT time scales, you need to have an understanding of the control algorithms that are being used in the inverters. And historically, the inverter manufacturers don't like giving those control algorithms out. So building an accurate EMT model for inverters is a challenge right now. Actually, our consortia, that unified consortia that I was talking about, has got a big effort, as well as there are several DOE projects that are looking at how to build better EMT models for inverters for these large-scale power system simulations. So we've started to do that for WEC, I believe. There's probably some information out there on that, but it's nowhere near where we've resolved all the problems that we need to fix on that. And again, that goes back to the fact that if the inverter manufacturers are using different control algorithms, they can have different fast response characteristics that can impact how you're actually modeling those. So a lot of work needs to be done in that space to standardize that compared to where we are with synchronous generators, as an example.
Great, excellent. So one comment is, a question is from students. Could you please comment on other energy storage forms like shift power to hydrogen compressed air energy storage and their potential for solving the balancing problem?
Yep, you'll notice that we did not include compressed air energy storage in there. The couple of reasons. One, for compressed air energy storage, you need to pair that with a natural gas plant. So if you're trying to get decarbonized systems, that doesn't help you out that much. It's just an improvement on the efficiency of natural gas plants. And they're very site specific. You need a very big geological formation to push that air into to pair that with a gas plant. There's been a couple of demos over the years that have looked at that. They haven't been all, I mean, they work, but they haven't necessarily proven to be cost effective. The hydrogen side stuff, we definitely see that as a way to do this long-term seasonal storage. I think we've done enough analysis that shows that when you start needing either over a day's long storage or into seasonal storage, that hydrogen can be cost effective. I'm not saying it is today because there's still a lot of work on getting all the pieces of that system together. But it could show promise, as well as the fact that you can then use hydrogen for multiple purposes. So you don't need to just convert it back to electricity. You could use it for ammonia production or for filling hydrogen vehicles. So there's this multi pathway stream of the hydrogen product once you make it. That being said, there is a lot of information out there looking at the hydrogen economy and all the parts of it. NREL has a lot of stuff on their website looking at sort of hydrogen at scale. If you Google hydrogen at scale, you'll probably find, a big chunk of material on that aspect. The problem right now is not really cost competitive today. We still have a ways to go to get all those pieces cost competitive. Okay.
Yep. Thank you, Ben. So we are running at the 12 o'clock, but I do have a question. And this is about, you discussed about balancing, you discussed about that energy storage is definitely expensive, right? What do you think the role of distribution connected resources, as well as, for example, electric vehicles, these are just, batteries on wheels, right, is going to be for us to lead to this transition? Do you think they're going to be effective? What needs to be done in this area, and what are your thoughts on that?
Yep. Okay. So, I think that accessing basically all of these ideas is going to be needed. as I kind of demonstrated the scale of how much energy storage we need, it's highly unlikely that we're just going to build 300 gigawatts of battery plants. I'm sure, Elon Musk would like to do that, and he'll sell them to us. But that's a lot. And tapping into things like electric vehicle charging regimes for shifting load resources around, doing a better job of preheating and pre-cooling buildings, doing all sorts of work. I think they're all actually going to be necessary for us to implement these very high levels of variable resource grids. So I think there's opportunity out there. We have to come up with other mechanisms also, though, to pay people for providing those services. And right now, we're just not set up to handle like large scale interactions of all these millions of devices asking for turning on, turning off, and getting reimbursed for that. But that's great, because that means the next 10 to 20 years is all going to be around the research to make that happen.
Thank you. So let me ask, are there any questions from the audience? You can unmute yourself and ask. Okay. If not, Thank you so much, Ben, for spending time with us today. It was a very informative presentation, and as usual, it's a pleasure to have you and talk to you. Um, uh, and with that, I will get this session to conclusion. Thank you again. Have a great day. Thanks everyone for joining.
Thank you very much. Thanks everyone. Bye.
Bye.